Ok, bueno, buenas tardes a todos. Antes de empezar, quiero agradecer a la Fundación BBVA por hacer posible este evento y a todos vosotros por acudir tan numerosos. La charla de hoy es parte del ciclo La ciencia en el cosmos, la ciencia del cosmos, que trata de astrofísica y cosmología. Y sin embargo, hoy no hablaremos solamente de astrofísica y cosmología, sino también de física de partículas. Ahora, como sabéis, la Fundación BBVA, además de esta serie, en estos meses está organizando otra serie dedicada al RAN 2 del LHC, el gran acelerador del CERN. Los de vosotros que habéis tenido la oportunidad de acudir a alguna de estas charlas, quizá os hayáis hecho la idea que la física de partículas, para progresar, necesita grandes máquinas capaces de acelerar partículas de materia ordinaria, electrones y protones, hasta las energías más altas que se puedan alcanzar, hacerlas chocar para que en el choque se produzcan partículas diferentes que luego son detectadas y estudiadas. Si son partículas que ya conocemos, las conocemos mejor. Si son partículas nuevas, nos ha tocado la lotería. Este es el gran descubrimiento. Y esto es absolutamente cierto, que la física de partículas necesita esto para avanzar, pero no es el fin de la historia. Hay otra rama de la física de partículas que no necesita acelerar partículas hasta energías muy altas porque no necesita crear nuevas partículas. Se dedica a estudiar partículas que ya existen muy abundantes en el universo. Lo que pasa es que estas partículas suelen ser muy elusivas y por lo tanto es difícil detectarlas y por lo tanto se conocen poco. Ahora bien, experimentos que buscan estas partículas, hay muchos de diferentes tipos, pero todos comparten alguna característica en común. Primero, tienen que ser grandes, porque como hemos dicho, estas partículas son elusivas, interaccionan muy pocos, y puesto que es fundamental que la partícula interaccione con el detector para que se hable de observación, cuanto más grande es el detector, más probable es que se consiga revelar una de estas partículas nuevas. Tienen que ser muy sensibles porque la probabilidad de observar una partícula, estas elusivas, es muy baja y no queremos perdernos nada. Tienen que ser muy precisos porque en el detector, en el ambiente, por muy limpio y preciso que se cree, por muy cuidado que se ponga, siempre va a haber partículas ordinarias, electrones, núcleos radiactivos, fotones, que son mucho menos que las partículas elusivas que queremos medir, pero son muchísimo más reactivas, interaccionan con muchísima más facilidad y cuando entran en el detector van a dejar una señal y el detector tiene que ser capaz de discriminar cuál señal es debida a partículas ordinarias que no nos interesan en ese contexto y cuántas son de las partículas que estamos buscando. Y justo por esta razón, por la necesidad de eliminar, de reducir cuanto más posible el background de estas partículas ordinarias, todos estos experimentos se meten muy bajo tierra, debajo de una montaña, para así filtrar cuanto más posible la contaminación de rayos cósmicos que continuamente bombardean la Tierra, que son partículas cargadas y que se entran en el detector, van a dejar un rastro perfectamente visible que puede cubrir el rastro que estamos buscando. Ahora bien, entre todas las categorías de experimentos que tienen lugar bajo tierra, voy a mencionar a dos categorías. Uno son los experimentos que buscan neutrinos, de los que a lo mejor habéis oído hablar en alguna conferencia anterior de esta serie. Por ejemplo, hubo una charla al respecto, me parece en mayo del 2014. Y otros detectores que buscan materia oscura. La materia oscura son partículas que sabemos que existen porque hemos observado en el cosmos sus efectos gravitatorios. Sabemos incluso que su contribución a la masa del universo es 5 veces la de la materia ordinaria de los bariones y sin embargo hasta ahora no hemos conseguido observar directamente ninguna de estas partículas. Así que hoy vamos a hablar de materia oscura y de qué podemos hacer para detectarla. Y para hacer esto contamos con la participación de la profesora Elena Aprile de la University of Columbia en New York, una de las más prestigiosas universidades americanas. Elena realizó sus estudios en Italia, se licenció en la Universidad de Nápoles. Ella entonces estuvo colaborando con el famoso Carlo Rubbia, que todos conocéis por el premio Nobel que obtuvo en el 84 por el descubrimiento de los bosones W y Z. Tras obtener su licenciatura en Nápoles, En el 78 se fue a Ginebra, donde hizo el doctorado bajo la supervisión de Roger Hess de la Universidad de Ginebra. Tras sacar el doctorado en el 82, se fue a Harvard de postdoc, donde se incorporó al grupo de Carlo Rubbia. Ahí estuvo trabajando del 83 al 86 y luego en el 86 se fue a la Universidad de Columbia, donde se encuentra hoy en día, con una plaza de assistant professor. Cabe mencionar que fue la primera mujer que se incorporó como profesor, como faculty member, en el Departamento de Física de la Universidad de Columbia. En el 91 pasó a ser associate professor, pero sin tenure, es decir, con un contrato no permanente. En el 96 obtuvo el contrato, el tenure, y en el 2001 fue full professor, lo que sería catedrático. Del 2003 a 2009 fue codirectora del Laboratorio de Astrofísica de la Universidad de Columbia. Ha recibido a lo largo de su carrera varios premios, empezando por una fellowship, una student fellowship del CERN, erogada en el 77, incluso antes de licenciarse, no hablamos de doctorarse, sino de licenciarse, que le permitió realizar una estancia al CERN, que fue cuando conoció y empezó a trabajar con Carlo Rubbia. Luego, en el 90, recibió un premio de la Japanese Society for the Promotion of Science. En el 91 tuvo un reconocimiento a la carrera por parte de la National Science Foundation. En el 2005 obtuvo la medalla de Ufficiale de la República Italiana, que es un importante reconocimiento otorgado por el presidente de la República Italiana en persona. En cuanto al trabajo de investigación, lo que ha caracterizado lo que es la área de experiencia de Elena es su actividad sobre detectores de gas nobles líquido. Empezó a trabajar con ellos directamente en el 77. Esto lo acompañó a lo largo de su carrera. Ha escrito un libro y ha escrito aproximadamente un centenar de artículos divulgativos, de artículos en revistas internacionales, perdón. Ha sido directora del 96 al 2000 del experimento LXE-GRID y desde 2001 es directora del experimento xenón, que es el del que nos va a hablar esta noche. Así que, sin más dilación, cedo la palabra a Elena.
Esta noche. What a beautiful language. Gracias. Thank you. Michaela, you said everything. Hello. Good evening. Hola a todos. Buenas tardes. I wish I could speak Spanish so well. So first I want to thank the Foundation for inviting me here, and I'm very happy to be here and share the excitement about my research with the people of Madrid, those of you here. Welcome. So the title or the focus of tonight's lecture is dark matter and liquid xenon detectors, which we use in experiment on Earth to detect it. So in the course of the 20th century, we have come to know almost nothing about this universe to knowing many of its basic features thanks to very precise observation on all angular scale. Michaela has made a great introduction about dark matter. Now I forget all about it. No. So when we say that we know that the universe in which we live is more than 95% unknown to us, we know it with great precision thanks to observation, let's say, from currently the Planck satellite is out there measuring the cosmic microwave background and many other observations in other areas. So we know very precisely that we are in a universe which is largely unknown to us. However, knowing is different from understanding, and that is the challenge which is before us today. As scientists, how can we resist to find out what this 95% of the universe is about? And the 95%, we will see a lot more later, is actually composed, when we say 95%, is dark matter and dark energy. The focus of tonight is dark matter. So this is the challenge that we face as scientists, and it's also the motivation for my research in dark matter. And so I will begin by telling you a little bit about how do we know that this dark matter is there, the existence of dark matter. And I will introduce you one of the methods Michele already mentioned, one of the methods that we use to find it, direct detection in experiments on Earth. Before spending a great deal of time on this stuff, which is the amazing liquid xenon that I love so much and why we use it, and then I will tell you about, for the large part of my talk, I hope, about the xenon experiment, the xenon one-ton experiment, a new experiment which is about to begin under the mountains of central Italy at the Gran Sasso Underground Laboratory. And this is the experiment that keeps me occupied all the time, preoccupied most of the time, but above all excited. I'm really excited, and the reason why me and my collaboration, and you should all also be excited about the Xenon one-ton experiment, is because not only is going to open a new chapter in the search for dark matter, as it's the first large-scale experiment that is going to begin in a few months, therefore very sensitive, with the sensitivity increase over what we have done so far of a factor of 100. So it's very sensitive, very powerful, and therefore with a lot of discovery potential if the so-called dark matter WIMP hypothesis is correct. But it's also exciting because of its timing. I pay a lot of attention to the fact that we need to be at the right place at the right time. Now is the time to dance, as we say, right? Because, as you know, and it was mentioned, we not only, the Xenon one-ton experiment will be there taking data while we have in Geneva at CERN, as you heard, this Large Hadron Collider, which is the most powerful accelerator that man has built, which is taking data with increased energy and luminosity with respect to the run that led to the discovery of the Higgs boson a few years ago, as you might have heard. So, one of the primary goals of the LHC experiments is to discover new particle, supersymmetric particle as predicted by the extension of the Standard Model via the supersymmetry theory. Among these supersymmetric particles, we have one that we love a lot, at least as dark matter hunter, the neutralino, the least supersymmetric particle, because it has all the right characteristics to be the ideal dark matter candidate. So the LHC is looking for dark matter. We have other experiments out there looking in the cosmos for dark matter indirectly. We have the EMS spectrometer on the space station. We have the Fermi satellite in the space. We have the ice cube experiment under the ice of the South Pole. These three big experiments that I mentioned are looking for dark matter indirectly by detecting the annihilation products, gamma rays, neutrinos, antiparticles, as dark matter particles annihilate with each other. And so we have these three approaches to look for dark matter, and I'm going to focus first on the direct detection. I'm going to focus, on the direct detection tonight with liquid xenon experiments. So let's first start with, I guess I wanted to say something that you already pointed out, that progress in this field, like in any other field of physics or of science, and the serendipitous discoveries that we make are usually associated with the progress in technology. I strongly believe that only by making progress in detectors, in accelerators, in technologies, we are going to make advancement. And this is what is driving me, actually, every day, every night. And that's the reason why I've been spending the last 10 or more years of my career perfecting this liquid xenon detector for the dark matter search. And I think every moment of it was worth it, because only by improving the detectors and the technology, by making it better, we can get closer to the truth. So I'm going to start with the first question. It works, that's nice. So let's start with the basic. What do we see when we look at the universe to begin with? So, looking at the sky on a clear night, we see thousands of glimmering light, and if we are lucky, we see the nebulous band of the Milky Way. We know that we live at the edge of this huge disc-shaped collection of stars, our own galaxy, with an extension of about 50,000 light years from the center to the edge of the visible stuff, right? And this is our Milky Way, but it's in 1924, our dear Edwin Hubble revolutionized or shocked a bit the world by saying that the Milky Way is not all what there is out there, right? Because there is much more than this galaxy. He showed that we have a lot of galaxies in the universe, and each galaxy is a collection of stars just like the Milky Way. And so, if we look at the universe, we see these myriads of galaxies, and these galaxies are not randomly distributed in the universe. They like to cluster. They like to be together and form clusters of galaxies, and together they form superclusters. And this is a simulation of the large-scale structure that we observe, actually, in the universe with all these voids and filaments. And all this stuff is kept together by the dark matter glue. The dark matter which fills the universe is the skeleton of the universe. Without dark matter, it will be very difficult to form galaxies. It will be very difficult to form planets, and therefore the solar system, and therefore to have life on Earth as we know it. Without dark matter, we will not be here. So how fundamental that is. This is the big question, what it is made of eventually. That's where we are getting at. So on the next slide, I show what is the stuff that the stars and the galaxies are made of. Everything we see, actually, everything we know of, is a combination. You can think of it as a combination of the same fundamental particles. We have the matter particles, the fermions from my dearest person, Enrico Fermi, and we have bosons, force particles, the force carriers. So this ordinary matter, the standard matter which makes me and you and the nice jambon of Spain, everything that we know is atomic matter, and the atoms, that's just a sketch of the atom, right, as we learned it in school, with this nucleus made of neutrons and protons bound together by the strong force, and this swarm of electrons flying around them, around the nucleus. So when I think about the atomic structure, which is the ordinary matter we know of, I cannot avoid putting up the periodic table and reminding you of the simplest atom that we know, which is the hydrogen atom with just one proton and one electron, one proton in the nucleus and one electron. But I want to profit from the periodic table up here to show you, to focus your attention on the right-hand side where you have the rare gases, noble gases, with the familiar helium maybe to you, with 2 protons, 2 neutrons, and 2 electrons. And down there we have the xenon, that I'm going to tell you a lot more about. It is one of the noble gases, a very heavy one. Heavier than xenon, actually, we have radon out here. And maybe you're more familiar with radon than with xenon, right? Radon is something, in fact, that I will come back to, because not only we don't want to have it around us and breathe it in our homes, but it's also going to be the showstopper, if I may say, for large-scale experiments for dark matter. It's radioactive, and minimizing and controlling radon in this next-generation experiment is going to be, let's say, the holy grail. Anyway, so this is about atoms. And together, these particles that I mentioned, the fermions and the bosons, together they make the standard model of particle physics. So we have this beautiful picture. We recognize these 3 families, the quarks, because the protons and neutrons that I mentioned, that you know, they make the atoms, are not fundamental particles. They're made of a combination of quarks. The up, the down, the charm and the strange quark, the top and the bottom. And then we have this family of the leptons. We recognize the electrons, the muon and the tau, with their associated neutrinos. This is the month of the neutrino. The Nobel Prize was given to Kajita and McDonald for the discovery of neutrino oscillation. I mean, that's another beautiful talk that we should give. But anyway, we have the neutrino, and then we have the gauge bosons. We have the force carriers. the gluon, which is responsible for the strong force, the photons for the electromagnetic force, and the W and Z was mentioned, another pair of Nobel Prize here for the weak force, and then the last, the Higgs boson, another, which completes now the standard model. So this is the picture that we have when the particle physics, the standard model particle physics, which works extremely well, except that it has some shortcomings, which supersymmetry, for instance, tries to fix. But let's move on. The question is these fermions, are these fermions and boson, are these standard model particle all that we see? Is that all is all that we see, all that there is in the universe? I already told you that that's not the case. This is the pie chart of the universe. The 95% I mentioned before is coming from these numbers, which are very precise numbers, especially from the latest ever more precise measurement, let's say, by the Planck satellite. So we have 68.3% in dark energy and 26.8% in dark matter, with the stuff that I mentioned, the ordinary matter, making just a mere 4.9%. So all what we know is just the end of this 4.9%, actually only 1% is in stars, and the beautiful thing that we see when we look at the sky. So the question then is, if the majority, or 85% of the matter in the universe is dark, how do we know it is there? That's the question I wanted to remind you about, the evidence of dark matter. And the evidence, we know that is there, this dark matter, through its gravitational effects. We said a little bit that already, but the most, I said that it's the glue that keeps everything together, is the backbone of the universe, but the measurements of the rotational velocity of stars in a galaxy at the galactic level since the 1970s, when Villa Rubin here systematically measured these rotational speeds of galaxies one after the other, the evidence for dark matter became quite accepted and very, very clear. So what is being done here, you know, you don't even have to know Newtonian mechanics or relativity or whatever. This is a galaxy, and the mass of the galaxy is concentrated in the center, and therefore you would expect that the stars which are closer to the center will spin faster than the stars which are out here to the edge, at the edges. So if you measure the rotational velocity here on the vertical axis, you would expect, or you would calculate, that the velocity would go down as a function of distance as you go far away from the center of the galaxy. On the contrary, however, galaxy after galaxy, rotational velocities are measured to be constant as a function of distance. And the fact that that this velocity is constant automatically means that there must be something out there which provides the gravitational pull on the stars, which are at the edges, right? As far away as you can measure. So the first evidence of dark matter comes from this. There is these stars in this galaxy spin at least 10 times faster than what you would expect if all what there is out there is visible. And from this we have the picture. The astronomer picture of the galaxy is more what is in here with this visible galactic disk, whereas an astroparticle physicist picture of a galaxy is this visible disk surrounded by a huge cloud of dark matter, a halo of dark matter surrounding this visible galaxy. And if you take our own Milky Way from, I mentioned already, the 50,000 light year in terms of distance from the center. Sorry, I forgot to say that 1 light year is the distance that the light travels in 1 year, which is about 10 trillion kilometers, right? So it's big, big distance we're talking tonight. But anyway, for the Milky Way, if we think of from the center of the Milky Way to the stellar disk, and I mentioned 50,000 light year, you can think of the dark matter halo of this galaxy in which we live to be at least 10 times larger, 650,000 light years or so. It's a huge spherical, we think of it as a spherical cloud of dark matter that surrounds each galaxy. And in fact, the question which right away comes, we know there are these galaxies from, so what about the mass of an entire cluster of galaxy? What about the mass of a galaxy cluster, where the extension now goes to million light years? And this is a picture from Hubble Space Telescope of a famous cluster, the Coma cluster, which was studied in the 1930s or so by Fred Zwicky, this Swiss-American astronomer, who, by studying the velocity of this galaxy in this cluster, he came to the conclusion that his observation could not be explained if all what there was the visible matter. And in fact, he made up the first name, dark matter, the Dunkelmaterie, from Zwicky. And so there is at least 10 times more mass in invisible than there is in visible matter from the study of galaxy cluster. And the question is, could we see directly, more directly, this dark matter somehow in the universe? We have seen, if I pause for a moment, we have seen the evidence at the galactic scale and the cluster of galaxy scale. Now the question I'm asking, could we see it? There is gravitational lensing, this phenomena which is predicted by Einstein's theory of general relativity, namely that the gravitational field of a galaxy or a cluster of galaxy deflects light. And the more mass you have, the greater the deflection. And so this is shown, the principle is shown in this sketch here on the right. If you are an observer here on Earth with your eye or your telescope and you're looking at this faraway object, this quasar, let's say, the light rays from the quasar to the telescope are going to be bent if in the middle, in between you and the quasar, there is a lens, there is a galaxy or a cluster of galaxy. So you will have multiple images, let's say image A and B in this sketch. And because we are in a three-dimensional space, you expect the light rays from these quasars to be on a cone, and the projection of a cone is going to be a circle or a ring. So you would expect to see the effect of lensing is going to be an Einstein ring, as we say as well. And in fact, on the left, actually, and the ring is going to be perfect only if your eye or your telescope and the lens or the galaxy are in line, which is not usually the case. So this is in fact an HST, an Hubble Space Telescope picture of a lensing event. And so the yellow images are the galaxies which are out there full of dark matter. And the lensing is this, what you see is the deformed image of these pieces, these arcs of a circle, which are the multiple image of this blue galaxy in the background, which is being lensed. Okay, so this is the closest as we get to seeing dark matter in the universe through gravitational lensing. And we can go one step further, and then I stop, namely that you can infer from the amount of distortion that you measure with lensing, you can infer the entire mass of the galaxy cluster. And in fact, this is a reconstructed image of the mass of the cluster, where the huge, smooth distribution here is the dark matter, and the number comes up very similar to what Zwicky came out with his study of the coma. And the spikes here are just the galaxies which are in between the object and the observer. So we can infer also the mass of a galaxy cluster through lensing. So let's come to the big question. So I hope I summarize quickly, sorry, I should pause more often, that dark matter exists. It was said many times. We know it very well, we know it very precisely. It's there. The big question is, what is it made of, right? That's what we are here to discuss tonight. And from all the stuff that we know, from all the knowledge that we know about this dark matter, we can say with very strong confidence that we know for sure dark matter is nothing like any of the particles of the Standard Model. None of them, none of those fermions, whatever that I showed you, boson, nothing makes can fit the bill for dark matter. We're looking for something beyond dark matter. Beyond Standard Model. That's why we say we are searching for physics beyond the Standard Model in our jargon. So the most popular idea, and before I forget, this is just one scenario, one hypothesis. The WIMP hypothesis is just one of many, okay? So don't get out of this room thinking that all what there is a WIMP. There is plenty of theories, smart ones like the ones we have also in this room, who have given us a zoo of candidates for dark matter, which range in mass from very, very light, like the axion, to very exotic, very heavy particle, WIMPs, and so on. I'm talking about the generic class of weakly interacting massive particle, the WIMP, the generic name we give to particles such as the neutralino or Kaluza-Klein photons in other models. And this is a particle which we have not detected yet, which is weakly interacting, as the name says, with ordinary matter, and that's what we're looking for. And from the amount of dark matter that we know is in the halo of our galaxy, because we can measure it and we know it very well, we can infer the density of dark matter particle in the solar neighborhood on Earth. How many of these particles reach us on Earth here? And we know that we are in a bath of dark matter particles as we speak here. There, billions of them are going through you, through me at every moment. And from the observation we have made so far and the fact that we haven't found any in experiments on Earth, we can say that only a few dark matter particles will care to hit a nucleus in your body, my body, let's say in 100 kilogram stuff in a year. We are looking for a signal which is a few events per 100 kilogram per year. Actually, we are pushing the envelope and looking for dark matter particle which gives you a rate, as we say, of a few events in thousands of kilograms per year. That's the sensitivity of the next stage experiments, such as the one I'm telling you soon about it. So I mentioned already that we have these three approaches to find WIMPs. If dark matter is in the form of weakly interacting massive particles, we can produce them, we can create them in the laboratory, and that's what is being done, I hope, at the LHC. So we produce them, we can observe them in the sky, and I mention it through the annihilation products with experiments such as the Fermi satellite looking for gamma ray from the annihilation of dark matter particles, or we can observe them in the laboratory as dark matter scatters off visible matter, such in a very low background detector, such as the one I'm going to tell you about. So I'm focusing on the last method here. We're going to look at the direct detection of WIMPs. And the principle is very simple there. We have a dark matter particle which scatters off a nucleus of an atom, and the nucleus gets a kick, this little energy, which we can calculate is an elastic scattering of a dark matter particle with a nucleon in the nucleus of an atom. So we can calculate the elastic scattering and know how much energy is imparted depending on which nucleus we're talking about and what is the mass of the particle. And this energy is very small. So we have an energy which is released in this elastic collision of WIMPs with nuclei, and that's what we are trying to detect with these detectors, deep underground, and I will tell you why we go deep underground. So in fact, I listed here a few or some of the main challenges that we have for WIMPs direct detection, right? Mentioned that the energy that we're looking for to measure is extremely small. We're talking of a few kilo electron volt in terms of, it's an energy, is the measure of is the unit of energy. We're looking for very small energy compared to the typical energy we usually deal with in a laboratory, from radioactivity. Forget about the huge energy at the LHC. When we deal with radioactivity, we're talking of millions electron volt of energy, typically. Very small energy, which means detectors have to have a threshold. They have to be able to probe, to sense such tiny energy. That's not very trivial because most of the detectors we developed are tailored to higher energy. They have to be, the signal from dark matter collision with atoms is extremely rare. I mentioned it's a few events per ton per year, let's say. This by itself is the main challenge. You need automatically, if you look at the rate, you can intuitively think that the more nuclei, the more atoms you put together, the better probability you have, the more probability you have for the scattering to occur. But making it big is not the answer. Big alone doesn't help. You need to be big and you need to be very quiet as well. You need to have very, very low background because the signal that we're looking for is hidden in this sea of background events, of radiation, which comes from all around us. Everything we touch, everything we use to build these experiments is radioactive. We are radioactive. I'm very radioactive tonight, actually. It feels like I'm radioactive. So we are radioactive. Everything we build stuff with is radioactive, and that's our challenge. I will not have time to tell you the pain in which we go through in selecting materials. But from every screw and nut that we use in the experiment I'm going to show you, from the pieces of steel and copper and Teflon that we use to build it, we just don't take it off the shelf, apart that we don't go to the supermarket. We carefully select this material after a very serious and extensive campaign of measurements. We take samples from a manufacturer of steels, of different samples of steel, and we measure painfully with the high sensitive spectrometer, germanium detector. We measure the radioactivity so that we can select only that piece of steel which has the lowest radioactivity. And it's not trivial to convince a steel producer, keep me aside these very big plates because I need them for my experiment. You have to measure very fast because he doesn't want to keep the plates of steel for you until you measure. That's just an example. So the way we deal with this problem of controlling or reducing radioactivity in the experiment is by carefully selecting the materials after measurements. At the same time, the first thing we do, we go underground, right? And this by itself is a challenge. It's not that nice or easy to operate an experiment under a mountain or in a cavern, in an abandoned mine, rather than being nice here. And if this were my laboratory, it would be great, right? So we go underground. That comes with a price as well. It's not that trivial. But we go underground. Why? Actually, I forgot to say. We go underground because with these thousands of meters of rock above us, if we are under a mountain, we attenuate the flux of cosmic rays. We are embedded also in cosmic rays, in neutrino, dark matter, it's everything around us. But the flux of cosmic rays, radiation, diminishes as we go deeper and deeper under the surface of the Earth. That's why we go underground, to minimize that cosmic radiation, which would give us actually the ultimate background that we don't want to have, which is neutrons. The background radiation that we care most to attenuate by going deep is actually the byproduct of cosmic ray interaction, which are neutrons. And neutrons, I forgot to mention, behave or give you a signal which is very similar to what a WIMP does. With the difference, in case I forgot to tell you, we have a way out, and that's where we win by going with large detector. A large detector like the xenon 1 ton, for instance, which has also position sensitivity, namely can tell you exactly where the interaction occurs, is powerful because a neutron, unlike a WIMP, will likely lose its energy in multiple spots, in multiple interaction, whereas a WIMP just comes in, boom, one interaction. So by having a technology which allows you to distinguish multiple site interaction from single site interaction, we win the game over the neutrons, at least in part, okay? Okay, so backtracking, we go underground, and I hope I explained why, to shield ourselves from cosmic ray. Then we have this radioactivity, and I told you a little bit the pain of trying to build stuff with low radioactive material to as large extent as we can. We shield this, despite going underground and making it low radioactive choices, we actually shield these experiments or detectors with additional stuff. And the material that we use most commonly today, as we scale up in size, we use water, actually, pure water. Water is a great shielding material, and we actually implement the water with, I will tell you later, in other way that we make it actually even more powerful as an active Cherenkov detector, another type of detector. So we shield the detectors, we make them all low radioactivity, and finally we rely on the ability of a detector to distinguish this famous WIMP interaction from a common background event. And we do that because we are lucky in a sense, because I mentioned it already, that the WIMP or the neutron likes to scatter off a nucleus of an atom, whereas the gamma ray from a potassium atom, radioactive, not the banana, but the potassium in the PMTs, whatever, radioactivity that you have around, gamma rays, beta particles, they scatter off the atomic electron. And because these two types of signal or radiation, if you like, scatter off these two different type of particle, a nucleon versus an electron, the signal that is resulting is actually different for the two different particles, and that's the basis of the discrimination. We can use the signals that we measure and compare them and use that distinction to separate a signal from the noise, from the background. I will make it more clear as we come to the next slide. Maybe the next slide is more clear. So what we have is an energy which is imparted to a nucleus, let's say a nucleon, because a WIMP kicked it, right? So this nucleus is moving because it has this tiny energy, moving very, very tinily, and this energy is what we have to measure. Now, any radiation in most matter results in three basic processes, if you like. One is that you have the vibration of the lattice of the crystal, if it is a crystal, right? You have phonon produced, or if you like, heat. So we can measure the phonon signal. We also expect that the energy released by WIMP interaction produces a certain number of ionization electrons, free charges, free electrons, that's the ionization signal. And we expect also that the same energy can excite the atoms and molecules of the matter, of the material, and this is the scintillation signal. So you can actually measure either one or the other, but the majority of the experiments which are searching for dark matter are clever enough, and most of them are using two of the signals simultaneously. They are able to detect simultaneously either phonon and ionization, such as the cryogenic dark matter search, which is using germanium and silicon crystals as dark matter target, and so they measure phonon and ionization, or such as the liquid xenon detector I'm going to tell you about, and all the other liquid xenon detectors which are on the market. They measure simultaneously the ionization and the scintillation produced in this material as radiation goes through. So by measuring these two signals, and by knowing that the ratio of these two signals is quite different if it's a neutron or WIMP, or if it's a gamma ray from background, we can discriminate the signal from the noise. And that's actually very important. Now, there is a bunch of names here. I don't want to run out of time, but this is the zoo of experiments that we have out there, searching for dark matter to show you. Maybe this is a race. You know that it's a race anyway. We all want to find dark matter, but I want to find it first anyway. But this is the worldwide map of the searches. I like to show them like this on a map where you see them clustered. The experiments, the names are the experiment name, and the yellow things are the laboratory around the world where these experiments are located. You find these experiments wherever there is a hole in the ground, to say not really, wherever there is an underground laboratory or a mine or a cavern to carry out the experiment. And so these experiments are located from as far as Japan with the X-mass experiment with liquid xenon, to China here where there is the deepest underground lab, to as far as here in Canada in the Snow Lab. This is where the experiment which was awarded together with the Kamioka, Super Kamiokande experiment is here in Kamioka mine. These are the two experiments that the Nobel Prize, where the two experiments which got the Nobel Prize for neutrino oscillation were located. So it goes all the way from Canada to China to the South Pole. There is a DMI's experiment. So all over the globe, right? And we are talking about the xenon experiment, which along some others is is the largest underground laboratory that the Italian built under the mountains of central Italy, of the Gran Sasso Mountains. And I'm going to show a picture then. Let's see, before I go on to the xenon, this is the state of the art of where we are today. It's a bit difficult. I didn't want to show many plots. I wanted to keep it simple, but this is the way, that's where we stand today in terms of direct detection of WIMPs from this variety of experiments that I mentioned. So what we see here essentially, you can take it because here is the cross-section, the interaction probability, the WIMP nucleon normalized by nucleon cross-section in square centimeter, and on the horizontal axis you have the mass of the hypothetical WIMP in unit of GeV over c squared, 1, 10, 100, 1,000 GeV, right? So all the stuff which is above this deepest green line, all this stuff above has been excluded. That's why we say it's an exclusion plot. We have not detected any particle, any WIMP particle to date. We have excluded a bunch of masses and interaction cross-section, right? And the best exclusion limits which have been placed to date are by the Xenon 100 experiment in 2012, and a year later by the Lux experiment, which is a similar detector, just with a much larger, with a bit larger active mass. So the xenon experiments have been leading the field of direct detection, and so that's when we say that there's a few events per 100 kilogram per year is corresponding to the best limit that we have been placing so far. So maybe it's too technical, but anyway, so we haven't found any particle yet. We have been able to exclude cross-section at the level of, let's say, a few times 10 to minus 45 square centimeter here. For a 100 GeV particle, the cross-section that we have been excluding a few times 10 to minus 45. So why xenon? Those experiments which have placed the best limits, which have given the best results or the most sensitivity to date, are liquid xenon-based detectors. So what's special with this xenon? The name from Greek, xeno, which means the stranger one, the foreign, the strange one, right? This is just a noble, one of the noble elements, as I mentioned already, is a heavy nucleus. We said that it has 54 protons in its nucleus. It has an atomic mass of 131, which means you have 77 neutrons, right? And it is surrounded by 5 shells. You know, the number of electrons per energy level, I don't want to make it complicated, but we have these five energy level with 2, 8, 18, 18, and 8 electrons in these closed shells of the xenon. Nucleus is a heavy, rare gas. It is odorless, colorless, it's very rare. In fact, it's one of the rarest elements on Earth, and this is one of the reasons, together with other, which I will tell you later, for its, let's say, higher cost than other noble gases. First, the density. First of all, sorry, the name or whatever, it was discovered by Ramsey, and because I put the name of Ramsey here, we got, chemists who got the Nobel Prize in recognition of his services in the discovery of the inert gaseous elements in air, and this determination of their place in the periodic system, in the periodic table that I showed you. We'll talk a moment about the application of xenon. Let's go to the few properties that I listed here. The density of the xenon is a gas. It's in the air that we breathe, and the density of xenon gas at standard temperature pressure is about 6 grams here per liter. However, when we make it liquid, as we use it in these experiments, and we condense it, we liquefy, the density of xenon around minus 100 degrees C or so in its liquid state is 3 kilograms per liter. So it becomes as 3 times denser than water, and this is one of the spectacular properties of this liquid. It's a very dense liquid, which together with the Iz, you know, the number of protons that we have in this nucleus is a large number, and the number of neutrons is large. The fact that the atomic number is so large means that the probability of a WIMP to scatter off so many nucleons is quite enhanced. And a heavy nucleus is better than a lighter nucleus for WIMP interaction, at least when they don't care about the spin. And that is the other feature of xenon, that it has actually, it doesn't come alone. It has all these siblings here, as I like to call them. There are 9 isotopes, and all these isotopes, many of these isotopes of xenon come actually with spin. And this is a good thing, because if the WIMPs would care to interact or care more about the spin of the nucleon, of a proton or a neutron, these neutron-rich isotopes of xenon, which are in the natural xenon that we use to fill the detectors, come very handy because we can probe the interaction of WIMPs with the spin, as well as spin-independent interaction. Okay, so now back to maybe his application. Dark matter hunters are not the only one who go after xenon. Actually, the application of xenon is in the lighting industry, you know, the xenon lamps in your car or the plasma, but also in the aerospace industry, and something that we don't mention too often, but xenon is known since 1940 to be a great narcotic, actually. It's a great anesthetic, with 1.5 times more efficiency than the nitrous oxide, which is a typical anesthetic used in medicine, and it has very little side effects compared to the standard anesthetics. So the main reason it's not so used in the medical field today is its cost, which eventually will change. The cost. Where does this xenon come from? I mentioned it's in the air that we breathe. It's a noble gas, it's in the air, so it's extracted from the air through the liquefaction of air. And as you liquefy air, you get nitrogen and oxygen. And in fact, liquid oxygen and the extraction of oxygen from the air is what drives the steel industry, because you need liquid oxygen for the steel production. Therefore, the production of xenon is strongly related to the economy, because if the economy is slow, the steel production goes down, and therefore the extraction plants are shut down. There is no need for liquid oxygen, which means there is no xenon either, because xenon comes as a fractional distillation of the liquid oxygen, which is extracted from the air for the steel industries. Wherever you have a steel production plant, you have also a big distillation tower to extract the oxygen which is needed. So the cost of xenon is strongly correlated with the economy. Of course, it's also strongly correlated with the fact that it's very, compared to the other stuff in the atmosphere, is very, very rare. The abundance of xenon in the air, as I mentioned before, is one of the rarest elements on Earth. There's only maybe 1 part of xenon in 10 million parts of air. The abundance is very, very tiny, the concentration of xenon, so by definition you have very little in the air that you breathe. So the cost is high. You don't find it on the shelf of the supermarket, as sometimes I say, and if you were to find it, it would cost you about $1,000 per kilogram. Not the cheapest stuff you find on the supermarket shelf. So that is an average price, and this is something you might want to keep. The price fluctuates a lot with the demand of various industries, with the production, as I said, of steel and the economy, but on average you can say $1 per kilogram is a good number. Not cheap, but still much cheaper than a lot of the other materials that, let's say, the cryogenic germanium and silica and the millikelvin materials that are used in other searches. That's why the attraction of this noble liquid, despite its rarity, it is actually much more cost-effective to put together thousands and thousands of kilograms of xenon. And you put it together actually in a very compact way, because remember what I told you, that the density of xenon liquid is 3 grams per cc, or is 3 times that of water. So 1 cubic meter of a pot of 1 cubic meter of volume, if I fill it with liquid xenon, gives me 3,000 kilograms already. So I can put my xenon 1-ton detector, which is about 1 cubic meter of volume, about on this table. We say tabletop experiment. Because of the density of liquid xenon and the fact that the number of protons in the nucleus is so large, makes it a very good absorber for radiation. You need only a few centimeters of liquid xenon to stop penetrating radiation. And that's another very strong feature of this material. I could go on and on. Let me see if I'm focused again. So that's all what there is on here. Maybe the boiling point, that's another good feature. The boiling point at minus 108 C. So when we make it, we take the bottles of xenon which we buy from the manufacturer, we turn the gases into liquid, we cool it down to a temperature of about minus 100 degrees C. That's something you can take. It's not so cold. It's cold, but it's not millikelvin temperature. It's not a very pushed temperature, and is such that is a temperature that we have learned how to master with the commercial cryocooler or refrigerator. You don't take your standard refrigerator, but it's a refrigerator which is readily available. So you can make it cold, you can keep it for a long time cold with these refrigerators which are commercially available. That's a major advantage with respect to other material which needs much colder temperature, the boiling point. There is a disadvantage that the melting point is very close. You see minus 108 versus minus 112, let's say, very few degrees only apart. And this means you have to be very careful in not going from liquid to solid, making xenon ice, which you don't put on your ice cream, but whatever. So that's why we actually typically operate at a little bit higher temperature, minus 100 degrees, minus 95 or so, in the detectors that we make, okay? But the best feature, the real reason we use xenon for dark matter, other than its availability with respect to cost and compared to other material, really is because it is the best material to give you a signal of ionization and scintillation. I don't want to say it's the best ionizer and scintillator among all the noble liquid, but that's what it is. If you look at the properties of liquid xenon and you try to use it in radiation, for radiation detection, you see that the signal that you get from radiation in liquid xenon is the highest in terms of ionization electron and scintillation photons compared to other liquid noble gases. Okay? And here in this cartoon that I have here is to tell you very schematically, I hope, the mechanisms through which the ionization electrons and the scintillation photons are produced when radiation goes through a liquid xenon material. So we mentioned already that we have a WIMP scattering off the nucleons of the nucleus of this atom, or maybe we have a gamma ray from radioactivity scattering off an electron. You have some energy release in this liquid xenon. What happens is that a fraction of that energy, quite a large fraction of that energy, actually goes into heat, which we don't measure in our detector. That energy is lost. But the energy that we measure is the one which goes into exciting the atoms and molecules, and through the excitation process, we get the de-excitation to the ground level of these states, and that leads to the production of light, we call scintillation light. And otherwise, we have, at the same time, we have also the ionization process which goes on. Namely, you have to kick one of these electrons, you make one electron free, and these free carriers, these free charges are the ones that we can measure through the ionization signal, the charge signal. So we talk about an S1 and an S2 signals in the picture that I will come with later. We have these two signals which are actually, as I mentioned already, quite large. And there is an additional process, the recombination process. Whenever there is an electron and an ion pair formed in liquid xenon, this electron likes to recombine very quickly with the parent ion, and this is the recombination process which we try to suppress by applying a very some energy through an electric field, for instance. But the recombination process also leads to the formation of excited states. So the source of light in xenon comes both from direct excitation of atoms and molecules and through the recombination process. And because of this, actually, the ratio of charge and light which we measure in liquid xenon is really strongly dependent on the type of our particle which came in. That's the discrimination power I told you. If it was a WIMP scattering off a nucleon, or if it was a gamma ray, we will see a different ratio of ionization and scintillation, which gives us the discrimination power we need to distinguish them. So how we do it, and this is how we do it, actually. I remember that song. This is how we do it, how we put it together, how do we measure these two signals in a detector which we call a time projection chamber. This is one of the things that I learned by starting to work with the Carlo Rubbia that you mentioned before. The idea of a time projection chamber goes back to Carlo with his seminal paper in 1977 when I began as a summer student at CERN. So what do? We take a certain amount of gas, we make it liquid, and we put it in a container. We need a container to contain a liquid. So we usually have a thermos, because the container is not just a piece of steel. We insulate it well from the outside so we can keep the liquid cold at minus 100 degrees C. So I will show you that the containers that we use are actually vacuum insulated, super insulated container, just like a thermos. So we have a vat of material, liquid xenon, and if we have an interaction of a WIMP or a gamma ray, we have this energy released. As a result of what I hope I showed you before, we have a bunch of ionization electrons produced, which we drift against the field. We apply an electric field across this layer of liquid by using very fancy electrodes that I will show you an example later to apply potential. So we have a cathode, we have an anode, we have some other grids in this medium. So the ionization electrons produced are separated from the parent ions through the electric field that we apply, and we drift them freely across the liquid. There is a catch, I have to say right now. One of the other challenges that this liquid, as you get it out of the bottles of gas, usually is not so clean. You have to make it super clean in the sense of removing not just the radioactivity, which we will say later, but also to remove molecules, atoms which are electron hungry, electronegative affinity very high. Let's say oxygen. Oxygen molecules are very bad. If you have oxygen in your liquid xenon, you don't drift anything because the oxygen likes to eat the electron, and you don't want to lose any of these small number of electrons that are produced by a WIMP interaction. So if the liquid can be purified and kept clean over time, the signal of ionization which is produced by a WIMP interaction can be detected. We drift the electrons across the liquid, and then we apply a trick. We apply the trick of amplifying, extracting the signal from the liquid to the gas, and as the electrons are extracted from the liquid to the gas, we actually give them another kick. We accelerate them in the gas by applying another electric field, much stronger, and as they accelerate in the gas, these electrons scintillate, produce more light. And that is why we change the signal of charge into a signal of light, which we detect with the same sensors that we use to detect the primary scintillation, what we call S1, the direct excitation, which is very fast and very prompt. In liquid xenon, this scintillation light is actually a few nanoseconds in terms of timing characteristics. Very, boom, T0, very fast. So the first thing which happens in the detector is a flash of light, which we detect as an S1, and then a delayed signal of charge, which we turn also into a light signal through the amplification in the gas. And therefore, we can use the same eyes in the top and the bottom of this vat. We place special eyes which can see the scintillation of the liquid xenon. And I didn't mention that the trick, or the challenge, sorry, not the trick, this light is not in the visible. The light which is produced as scintillation in liquid xenon is in the very deep ultraviolet. We cannot use more commercially available photomultipliers, as we call them. This is a beautiful detector. The photomultiplier is a detector of light, right? But we cannot use commercially available tubes because we have to have special photomultiplier which are developed not only to withstand minus 100 degrees and some bars of pressure, but also to see in this very deep UV region where the light is emitted from xenon. But maybe if I skip this complexity, we have made a lot of progress over the last 10 years that we have available eyes, phototubes, which can see in the deep UV of liquid xenon. We place them on the top and the bottom of this container filled with liquid xenon, and we use the same type of detector to measure the prompt scintillation and the secondary scintillation, which is proportional to the energy of the interaction. So that's how we do it. That's how we measure the two signals simultaneously, and the ratio, as I mentioned over and over, of these two signals is quite different. It's much, much smaller for a WIMP interaction than it is for a gamma event of the same energy. That's the discrimination power in liquid xenon. And maybe you can keep as a question, because maybe I give you hints. Why do I put them on top and bottom, and I can answer you later. Why the photomultipliers are placed on top and the bottom. Anyway, whatever. I'll tell you later. So I hope I gave you the principle of why we call it time projection chamber is a good point. Sorry, I forgot to mention the power of this detector is not just that it can measure the energy of this interaction through the measurement of these two signals. From these two signals, we can infer the energy which was deposited in the liquid, but we can see where it happened because we have a three-dimensional position-sensitive detector, as we say correctly. The three dimensions come from the following. First of all, the distance between these two signals, the drift time that we measure. We measure the time that the electron takes from this point, let's say, up to here, where it's drifted. That time is proportional to the distance, if I know the drift velocity with which these electrons move in the liquid. So I have the one coordinate, the depth of the interaction in the liquid. The other two coordinates in space are inferred from the pattern of light that I measure on this ice, on these phototubes on top. So we have X, Y, and Z position. We have 3D image. We have a 3D imaging detector through the measurement of the time and the measurement of the X and Y coordinates from the pattern of light on this phototube. I hope I gave you at least a feel of what we do. But this is how we do it, and this is the principle of detection of several experiments, not just the xenon experiment that I'm going. Now I'm almost finished. I'll show you just a bunch of beautiful pictures as I try to wrap up. Sorry, probably I'm taking too much time. So that's the principle of the xenon dark matter program, the principle of detection, which started in about 2005 or so, with the first prototype, which had only 25 kilograms of mass and 15 centimeter drift across the layer. And then we wanted to be better, and we built the Xenon 100 detector with 30 centimeters of drift and about 160 kilograms of xenon total. And this detector is still in operation at the Gran Sasso laboratory, and I will tell you a bit of this one, which is the latest of the family. We dare to go 3 times longer, 100 centimeters of drift and 3,300 kilograms in the first phase, and in a second phase within the next 5 years or so, we are going to put 7,000 kilograms in the same detector, making it just the pot larger. So we want definitely to go fast with our race for dark matter with the Xenon program. And just to give you an idea of how these eyes, these phototubes that I mentioned all in a sketch, this is a Xenon 100 detector, which is actually quite beautiful. And this is a photo of the top array of PMTs in the Xenon 100 detector, which is still running. And this is the bottom PMT array. Just to point out that these photomultipliers that we developed together with the manufacturer back more than 5 years ago are special type. You see that they're very small, 2 by 2. 2.5 by 2.5 centimeter squares, so 1 inch square photomultiplier, metal channel, which means it's only 3.5 or so centimeter tall. They're very tiny eyes, but they're working beautifully. They're sitting in liquid xenon at minus 100 degrees or something since 2007, and they're still working, which is a success of the technology. But for the next generation, we wanted to have even better things. So we're going with bigger photomultipliers, which are actually even more sensitive than these little ones. So the Xenon 100 detector is these 2 arrays of PMTs, top and bottom, and you will see a lot of white stuff, which is the Teflon. We use a lot of Teflon in these detectors because Teflon is a good reflector for the VUV light. We want to reflect all this light, which is resulting from a WIMP interaction or other interaction, and try to catch as much light as possible. We use that reflector. And then I mentioned that we apply potentials to create an electric field. In xenon 100, we have 16,000 volt on the cathode below and about positive 4,500 volt on the anode to create the electric field for the drift, and so on and so forth. And this is just an example of how the WIMP particle of this energy, for example, the energy recoiling energy would be 9 keV, how a WIMP event would look in xenon 100, let's say. I mentioned this 3D position reconstruction. I wanted to give you a feel. These are now actual measurements. These are actual signal that we measure one event in xenon 100, the S1, the light and the charge signal measured, and the drift time of the electrons. And notice that we are talking about a handful of electrons. In this case, it's 32 electrons drifting. And this is how the pattern recognition on the top PMT array will tell you where in X and Y the interaction was, just to give you a feel of what it means, a three-dimensional position-sensitive detector. And how powerful it is, I guess I missed to mention that if you have a container filled with liquid xenon and you can see X, Y, and Z for every event that you measure, you actually have the luxury to select only certain volumes within the pot that you have, to reject background, because background, let's say, is coming mostly from the walls of the container, from the PMTs themselves. They're radioactive. As I mentioned, everything is radioactive. That radiation, which comes from top, bottom, sides, can be cut by doing a fiducialization, as we say, of the volume. So by having this capability of 3D position-sensitive detector, we can fiducialize the volume and keep only the core, the central region of liquid xenon clean. Clean means free of background. So, because one of the main challenges we have is to reduce the background, I wanted to make the connection that the 3D position sensitivity allows you, if you have this big thing, to cut until you get the center region, which is quite free of background, and win over others. So, xenon is underground, as I said, at the Gran Sasso Laboratory. That's just a photo. And to tell you that from time to time we also go skiing, because there's beautiful mountains and there is beautiful towns. The Asergi village is just beautiful, but we spend a lot of time just under, we spend a lot of time under this tunnel, but we also go hiking. It's a beautiful place to be, and that's under this tunnel that the lab is built. The lab is a large lab, I told you already. There are 3 big caverns, let's call them cavern. There are experimental halls, which are actually quite nice to work in. It's not very different than going to my Columbia lab. It's just a lot colder down there, and it's humid. But it doesn't feel like so strange, actually. You drive to this 10-kilometer tunnel, you turn to the right, and you are underground. When you say you're underground, it sounds scary, but it's actually a nice place to do physics. So here is the location of the xenon 100. It takes a very little space, and this is where the xenon 1 ton is now located, in the central gallery, in the central hall, the hall B of the Gran Sasso lab. We have about 1,400 meters of rock above, and this is what is shielding the experiment from cosmic rays. So now I have mostly a bunch of pictures. The collaboration, who is doing this work? I'm not doing it alone. It started with a small group of people, and now we have grown to be about 125 scientists from 20 institutions, a lot of students, a lot of young researchers, and it's a beautiful feeling to see your former students becoming postdoc at this other institution, maybe actually a competing institution, working for a competing experiment, but then eventually becoming faculty members, some university in there. We recycle them, we move them around. The expertise is too valuable, and we try to keep it within the collaboration. But we have a lot of institutions. This is the institutions which make xenon 1 ton right now, quite a few around the world, from the US to Israel to Abu Dhabi to France, Germany, there is Portugal. We don't have Spain, unfortunately, but everywhere, France, Switzerland, Germany, I mentioned. And so we move them around. So it's not that difficult to find them a position here and there. We try to keep them. In fact, one is in the audience, I recognize, and is working for a competing experiment at the Canfranc. I forgot to mention one of those laboratories right here in Spain, the Canfranc laboratory. And a former postdoc of mine, an Italian, is sitting down there working for a liquid argon experiment of the son of Carlo Rubbia. Since we spoke about Carlo, we speak also about Andre. So there is Roberto, Roberto working at CMAT on argon DM, one of the liquid argon experiments for dark matter. So it's a pleasure to see these young people and keep them excited about what we are doing. And I think they're all very excited because we are building the Xeno 1 ton. That's where it is, the sketch of the Xeno 1 ton experiment. I'll try to go fast because maybe I'm taking too much time. Just to tell you that in 2000, this is very fast development. In 2013, this is the whole B of the Gran Sasso. There was nothing, just the sign of the water tank where we put this shielding material. And then it took very quickly to build the tank. So we have this 700 cubic meter of water, which we instrument with PMT to shield the detector. In the center of the tank, there is the liquid xenon detector. And next to the water tank, as we call it, there is the infrastructure building. We built this a 3-story high building. We are talking about a tank which is about 10 meter high and 10 meter diameter. Sorry, I forgot to put the dimensions. It's not a small baby, but the whole B is very tall. This is an actual photo of the whole B. Icarus, the Icarus experiment was back there, actually, for those of you who have heard that name, of Carlo Rubbia, speaking of Carlo again. So the tank is 10 meter or so high, 10 meter diameter, and this is the building. It's 3 stories, and it's not that it's missing the windows or the doors or whatever. It's actually made of glass. I had the vision to show people what are the beautiful things that we make and what we use for Xeno 1 ton. So there's all glass. It's all glass covered. So if you visit the underground lab one day, I hope you come to see Xeno 1 ton, you can see from outside all this beautiful equipment which is needed to operate the experiment underground. And this is the first one, and I'm sure it's not going to be the last because it was a great idea. I like it. So that is the location. So this was, November of last year, okay? It was very quick, and the building is almost filled. So I'm going to show you a few of the equipment or the systems that we had to develop and build in order for making Xeno 1 ton possible. That's, I think, what I'm going to do. So in a sketch, again, just for you to understand, this is the shielding, the water tank, as we call it, that we use water for shielding, about 4.5 meter water. This is the detector hanging in the center of this water container. The water, as I mentioned, is not just, it's pure water, but it's not passive. It's instrumented to be a muon veto detector to detect the muons which come still at that depth. We still have muons and we want to catch them. We want to throw them out. We want to throw the event if there is a muon detected by the muon veto. The central detector is the one in the middle there. The liquid xenon is filled through this cryogenic pipe from this system, which is the cryogenic and purification system, which is sitting at the top here of the building. In the middle floor, we have all the electronics and the EE.UU, the data acquisition system of the experiment. And on the lower floor, we have two systems which are just beautiful and dedicated to Xeno 1 ton. One is a storage vessel, a storage bottle for containing all that precious liquid xenon that we need. And the other is a column, a 5 meter tall distillation column, which actually is used to cryogenically separate the tiny fraction of krypton which is left in xenon. One of the byproducts of the distillation is that xenon doesn't come alone. It has a tiny, tiny amount of krypton, which wouldn't be a problem other than there is one isotope of krypton which is radioactive, the krypton 85. And so we need to reduce the krypton 85 radioactivity to unprecedented low level, and we do it by cryogenic distillation. We pass the liquid, the gas actually through this column and use the different vapor pressure of krypton and xenon to separate the two before we fill it in the detector. I hope I was clear enough. So I will show you some pictures of some of this system. This is how, that was the sketch. This is how it looks like with this storage bottle, the column, and the cryogenic system. Just the beauty is the central detector. I say simply beautiful. It's true. It's a work of art. That's a sketch of it. We are putting it together as I speak. And I guess I have a few pictures. This is the field cage. All this copper that you see are the copper. And this is Laura. Yes, you recognize her. These are my friend, collaborator, Laura, Professor Barth at the University of Zurich, and some of her team, which have developed the shaping rings, the copper rings, to shape the field across the 1 meter. One picture, but the other picture is also nice. I mentioned that this is now looking from the top, and you see this Teflon reflector, which is actually, you see, it's almost like a mirror, because you see the reflections there, right? So inside the WIMP, when he goes into this vat filled with liquid xenon and Teflon, he will see just all this white stuff. That's the interior of the TPC, okay, eventually. Of course, the TPC itself, the structure, the detector is contained in the bottle, as I mentioned, in the vat. And this is a picture of the cryostat that we were responsible at Columbia. Actually, this is another, in my mind, nice piece of work, is a double-walled, as I mentioned, like a thermos, selected stainless steel, low radioactivity stainless steel cryostat. Cryostat means that it keeps the xenon cold. Maybe we see, to give you an idea, I have to show off, that's Elena everywhere, because I've been following the construction of the experiment from the beginning, also as a technical coordinator, so knowing every detail gets you a bit crazy, but I am a bit crazy, it's okay. But that's the size of the flange of the outer vessel, and that's the size of before it was finally machined. This is the way it looks when it is actually electropolished and moved underground, right? And this is again me at the company, one company in Italy with whom we built this thing, wrapping the baby, as I say, putting like 30 layers of mylar to produce what we say super insulation. Vacuum doesn't do it alone. We wrap the inner vessel with a lot of layers of mylar, and then we pump vacuum in between the outer and the inner vessel to keep the xenon cold, okay? That's just to give an idea of the size, and maybe it's clear here, again, to give you the size. This is the inner vessel. The liquid xenon is contained in this vessel. This is the flange that I showed you before, the outer vessel flange. And before we close it, we wrap it. And so we wrap up also this, because I'm running out of time. These are just beautiful pictures of the experiment. And one picture about the eyes, the beautiful eyes I mentioned, and these photomultipliers. These are the photomultipliers for xenon 1 ton. They're much longer and 3 inch in diameter instead of 1 inch square. So this is the photomultiplier array. These are some of the electrodes I mentioned, these fine grids, 200 micron diameter wires that we stretch across 1 meter. This is the xenon gas. It takes 600,000 liters of gas to fill the detector. And this is the special sphere that I'm very proud. It's another piece of a beautiful work because it's actually a high pressure vessel. It can keep the xenon at 70 bar, but it can keep it also cold at liquid nitrogen temperature. So this is just of the picture. It's 2.1 meter in diameter. It's again double-walled stainless steel sphere. It can store 7,600 kilograms of xenon in either gas or liquid, and this is how it looks after it's electropolished. This is one of the 2 semispheres. You put the 2 together with one big weld. We are talking about 3 centimeter thick stainless steel here to keep this pressure. It's not a thin piece of steel. But that's how it looks eventually when it was delivered last August, 1 year ago. And this is the actual picture of the so-called storage and recovery system for xenon 1 ton. That's a very important piece of apparatus which was developed just for this experiment because we need to a lot of the value of the experiment is in the liquid xenon and in the photomultiplier. So we cannot afford to lose it. So we need to store it safely and cleanly. So I think that's the last picture. Maybe I skipped the cryogenic system, which is the bunch of refrigerators and a lot of ultra vacuum equipment that we use. This is all custom made. That's maybe a comment that this you don't buy off the shelf. You design it with your student, your engineers, your postdocs. You make a design, you build it with smaller company. That's what is actually the excitement about this experiment, that the people who work with this experiment are actually engaged in making it. It's not just something you buy. You make every piece of it, and it's actually an amazing work, but it's also very rewarding for the young people who work on it, actually. We make them expert in different areas. So that's on top of the platform of the cryogenic system. And here's my last slide, which I don't have to read. Maybe I take the time to show you at the end of this talk. I have a 3-minute movie that maybe I can play. The summary is, it's very simple. Dark matter is still a big question, and we know that there is a lot of it out there. And if the WIMP hypothesis is the right one, this next generation of experiments, starting with xenon 1 ton, and the others which will follow, have a great chance to detect it. That's the message I would like you to go away. And I will show you a short video that the team has put together just to give you a feel of this construction phase of the experiment. And I will reduce the sound. Oh, they reduced the sound. Maybe I speak but now that I showed you all those photos and told you things, you should be able to realize that was the entrance of the lab, and this is that empty circle, and I'm wondering what the hell will happen. That was in 2013. And this is the early construction of the beams which make this building, let's call it the building, and the water tank construction come next. That's the big structures that we had to put together. But what I didn't mention is all the R&D which goes on at all these universities. This was Columbia University, this is my group there. But in all other universities collaborating with us, there is a lot of work still going on, as we say, research and development, trying to understand different aspects of the experiment, and keeping, that is Laura, keeping these young people actually engaged and giving them expertise is also a way to make them learn about the liquid xenon technology. So you have R&D facilities everywhere in these various universities which participate in xenon. That was in Germany. This is a group meeting, and we have a lot of group meetings. We try to meet wherever we can, but a lot of time at Gran Sasso actually. And this is this fast time lapse of the construction of this large structure, which is this water container. In fact, that's an interesting story. You can imagine how you build this big tank of 10-meter diameter in an underground location. You build it circle by circle. You start from the top and then you lift it up. You put another circle, you weld it and move it up until you get to the bottom. It's top to bottom, not bottom down. So then the tank is built. These are the phototubes that I told you about, and some of the research about photomultipliers, this new type of photomultipliers, this is Teresa, she's Spanish. Yes, Teresa Marudan. She's now in Germany, however, you lost her. She's a great scientist. These are my students. I forgot to mention the demonstrator, the xenon 1 ton demonstrator at Columbia, which laid the basis for the cryogenic system that we built. Actually, that's one of the systems we built in the US. A lot of the stuff was built, of course, on site, in Italy, to avoid all this shipping. And this I like, this moving that 9-meter, 8-meter diameter pipe which allows us to put the liquid from the top of the building into the detector. You might ask me the question, you wonder why the hell you don't put the liquid, the cryogenic or the coolers next to the detector. For radioactivity, right? To minimize radioactivity, you cannot buy commercial cryocooler and have them radioactive free as well. It will cost too much. It will take tens of years. So we place the radioactivity which comes from the refrigerator far away from the detector. That's why it's cooling at a distance, as I call it. We put the refrigerator in the top room and then we feed the liquids in through that long insulated pipe that you have seen, which barely made it into the tank. And that's why I like that picture, because we measure it and by tens of centimeters we made it in. I guess that's the end. Thank you so much for listening.